Welcome to Discrete Mathematics. Today we are going to explore a fascinating concept called bottom and top elements. Imagine a massive corporation where the CEO sits at the very top and a brand new intern sits at the very bottom. We are going to see how mathematics uses this exact same idea to find the absolute extremes in ordered collections. Now that we have our corporate analogy, let us look at how this works mathematically. We start with a partially ordered set, or POSET for short. This is simply a collection of items combined with a specific rule to compare them, like is less than or equal to. In such a set, the bottom element acts as the universal starting point that everything else grows from. Conversely, the top element is the universal ceiling that nothing can go beyond. Keep in mind, a set does not strictly have to possess a top or a bottom. Sometimes the hierarchy just goes on forever. Building on that foundation, let us look at the formal mathematical definition of a bottom element. The formula states that for every item x inside our set P, the bottom element is less than or equal to x. The symbol that looks like an upside-down T represents this bottom element. If you change the items in the set, the specific bottom element might change, but its fundamental role as the absolute lowest point remains exactly the same. As the set grows, it is always smaller than or equal to every single new addition. Similarly, this formula defines the top element. Notice how the position of x has swapped compared to the previous formula. Instead of the special element being smaller than x, now x is always smaller than or equal to the special element, represented by the regular T symbol. As the set grows larger, the top element must be greater than or equal to every new addition. Otherwise, it loses its status as the absolute top. This ceiling ensures that no matter what item you pick, it will never exceed this maximum boundary. Before we move on to any proofs, let us see this with a concrete example using sets. Suppose we have a main group of two letters, A and B. We want to find the top and bottom elements of its power set. The power set is simply the collection of all possible smaller groups you can form. Our comparison rule here is a subset of. Step by step, we build the power set, which gives us 4 items. The empty set, a set with just A set with just B, and the full set containing both. Continuing with our power set, we need to identify the extremes. In set theory, the empty set is considered a subset of every single set in existence. Because it is a subset of every other item in our collection, it perfectly fits the definition of the bottom element. On the other hand, every single group we created is entirely contained within the original full group. Therefore, the full group is the absolute ceiling. This means the empty set is our bottom and the original set itself is our top. Let us try a different kind of example, using numbers and division. Consider the set of all positive numbers that divide perfectly into the number 12 without leaving a remainder. Our comparison rule this time will be divides into. This means we consider a number to be less than or equal to another number only if it divides perfectly into it. We list out our collection of numbers, which are 1, 2, 3, 4, 6, and 12. We will use this list to find our absolute extremes. Now we need to find our extremes for this divisibility set. We know from basic arithmetic that the number 1 divides perfectly into every single whole number. Therefore, 1 divides into everything in our list, making it the bottom element. Conversely, by the very definition of how we built this collection, every single number in our list was chosen specifically because it divides perfectly into 12. Thus, 12 sits at the absolute peak of this specific hierarchy, acting as our top element. To make this divisibility example even clearer, let us look at a visual representation called a Hasse diagram. This is a way to draw hierarchies without drawing every single overlapping line. Notice how the number 1 sits at the absolute lowest point, with lines branching upward to everything else. This visually confirms it is the bottom element. Similarly, notice how all lines eventually merge upward into the number 12 at the absolute peak, confirming it is the top element. Now that we have seen formulas and examples, a very important question arises. Can a set have more than one bottom element? The answer is no, and we can prove this mathematically. Let us prove that a set can only have one bottom element by pretending it has two, which we will call B1 and B2. Because B1 is a bottom element, the definition says it must be less than or equal to absolutely everything, including B2. Looking at it from the other perspective, since B2 is also a bottom element, it must be less than or equal to B1. This brings us to the final step of our proof. We have established that B1 is less than or equal to B2 and B2 is less than or equal to B1. In ordered sets, a mathematical property called antisymmetry forces them to be the exact same thing. Therefore, B1 equals B2. This proves that it is impossible to have two different bottom elements in any given set. If you think you have found two, they are actually just the same item. The exact same logic applies to prove that the top element is also completely unique. So we have proven that these extremes are unique. This brings us to why understanding top and bottom elements is incredibly important in the real world, particularly in computer science and logic. When you write an algorithm to find the maximum or minimum value in a list of data, you often have to initialize your starting variables using the absolute top or bottom elements of that data type. In digital logic and circuit design, the bottom element represents false or zero voltage, while the top element represents true or high voltage. Without these absolute boundaries, computers could not make reliable decisions. To wrap up our exploration, let us review the most important ideas. The bottom and top elements represent the absolute extremes of an ordered collection. The bottom element acts as the universal foundation, being smaller than or equal to everything else. The top element acts as the universal ceiling, being greater than or equal to everything else. While not every collection has them, when they do exist, they provide crucial boundaries that help us understand the structure and limits of the entire system. You now have a solid understanding of top and bottom elements.